Hello, everyone. I want to talk briefly today about half-life. Half-life is related to kinetics, and it's an important way of expressing some things in kinetics that you'll see a lot in many applications. We'll actually see this come up again in a later chapter. Some of you might associate Half-Life with. I know there was a video game once with that name. Maybe that is telling you how old I am. But you might associate it with nuclear chemistry, and that's something we'll get to in a later chapter. Half-life is something that's true for any reaction that's occurring that we care about the kinetics, and we'll come back in the later chapter and talk about why it's important specifically for nuclear reactions. So the half-life of a reaction is the time it takes for the concentration of the reactants to fall to half of their initial value. So the time it takes for them to be cut in half. The half-life, as we've kind of alluded to on some of the slides we've looked at already, is dependent on the order of the reaction. So I want to look at that again. So this table from your textbook is summarizing many of the things we saw related to the integrated rate law. So we're showing the order, the rate law, the integrated rate law, and then the half-life expression. We are going to be focusing specifically on one type of reaction here, and that is the first order reaction. This is the reaction where we really care a lot about half-life, and we'll see why that is. So although there is a half-life expression for zero order and second order, it's really the most useful, as we'll see, for a first order reaction. And in fact, I want to talk through how we get from the integrated rate law to the half-life expression for a first order reaction. So if you think about what half-life means, so it's the time necessary to go to half of the initial concentration, and we go ahead and take the integrated rate law. We could put in some numbers here for initial and concentration at time t. So let's maybe have a default of 1 for the initial, and then at time t it would be half of that. So we would have the natural log of 1/2 over 1 is equal to negative kt. So we have basically the natural log of 1/2. We have a negative sign. We can use some rules for logarithms to basically flip that over. So we get the natural log of 2 is equal to kt if we were to do that. And then if we take the natural log of 2, we get this number 0.693. So that's where that number comes from. And then we divide by k. So we have the half-life is equal to 0.693 divided by k. So that might seem, you might wonder, well, why do we care about the 0.693? Where does that come from? That is where that number comes from. The important thing about this relationship is that it is a constant. So 0.693 is a constant, k is a constant. This is not changing. We can't do really anything to change this value. Whereas you can see for the half-life expressions for zero order and second order, they are dependent upon the concentration. First order is independent of concentration. And that's kind of a big deal, as we'll see. So what this means for a first order reaction is that the time it takes to go to half of any given concentration is a constant that we call the half-life. So we can see here for this example, so we'll say concentration of 1 to start with, and to get down to a concentration of 1/2 would be 1 half-life, whatever that half-life happens to be. So it's 1 half-life for that to occur. And then starting at 0.5, if we cut that in half, we get 0.25. So that half-life we're showing here, so from 0.5 to 0.25 is an additional half-life. And then from 0.25, half of that would be 0.125 down here. So that is a third half-life. So we cut it in half each time. And so essentially we can see how that's slowing down. You might imagine if you're standing next to a wall, if you take a step maybe you step halfway to the wall, and then from there you step halfway again. So each step is getting shorter and shorter and shorter as you get closer to the end, which is the wall. So each of these steps here, as we move along, is getting shorter and shorter. So by shorter and shorter, I mean the length of, or the difference in concentration is getting smaller and smaller, but each time length is the same. So eventually, this will get so small that maybe you have, one molecule left, and then at some point it goes away. So eventually it does go to zero. We can't divide infinitely, even with atoms. Eventually we get down to one atom. But that's the essence of what goes on with half-life. So let's go ahead and look at an example. So again, this is important with nuclear chemistry, as we'll see in a few chapters. A radioactive substance that decays according to first order kinetics has a concentration of 0.55 molar and a half-life of 2.5 years. If the accepted safety threshold of this substance is 0.01 molar, how long until it can be safely disposed of? Okay, so that is the question. Go ahead, maybe pause the recording, see if you can figure out how to do that, and then when you come back, we'll go through it together. Okay, so let's go ahead and discuss what to do here. So we see it's a half-life question, so we know that this is true. So T of 1/2 is equal to 0.693 divided by K. So that is true. So we know the half-life, and half-life again is how long it takes to get halfway there. And we could find K if we wanted to do that with this equation. And let's go ahead and put that in. So this is equal to 2.5 years. One way we could do this, we're actually going to do this in two ways. So one thing we could do is we could see, well, how long does that take if we cut it in half? So we'll start with a 0.55, and we'll divide that by 2. I'm going to go ahead and open a calculator so we can do the math. To get down to 0.01, the math could get a little bit involved. So we'll open a calculator so we can see as we go through that. So 0.55 divided by 2, and we get this number. So I'm going to do it like this. So we get to 0.275, and that's one half-life. And then we're going to do it again. So we get to 0.1375, that's another half-life. And then we do it again. We get to 0.06875. Okay, we're not quite there yet, so we'll do it again. And there, I'm going to come up here. As we're running out of space, we get to 0.034. I'm just going to put 0.344 for now. We do it again. We get to 0.0172, and then we do it again, and we get to 0.00859. We were looking for, let me put this out of the way, 0.01. This is finally below what we wanted. So that's below 0.01. So we have 1, 2, 3, 4, 5, 6. So that was 6 half-lives to get there. So we would take 6 times 2.5 to get our answer. So let's go ahead and do that. Okay. So that gives us 15 years. Okay. Now that is actually an estimate. That is not exactly how long it takes because this is not 0.01, it's a number less than that. This is not 0.01, it's a number bigger than that. So it's somewhere between 12 and a half and 15 years. So this is not an exact number. This method works very well when you know you have a whole number of half-lives. So if you have a question that you're asked, how many half-lives, uh, um, or actually, let's reword that. So if you have a question that says, in 3 half-lives, what is the new concentration? So if you happen to know that, or if it says, for this one, if it says after 5 years, well, you can easily see that that would be 2 half-lives. So if you have a whole number of half-lives, this is a good way to do this problem. Some of you may have seen something like this in the Chemistry 3A course, and that works great for that course. However, there might be times like this where we actually want a very specific number, and the 15 isn't quite good enough for that. So what we'll do for that is we will look at this equation. So we need to use this equation if it happens to be less than a full half-life. So this is what we'll be using. So natural log of concentration divided by initial is equal to negative KT. Okay, so let's go ahead and write that down. So natural log of the concentration at time t divided by the initial concentration, I guess the knot should be on the outside of that, is equal to negative KT. Okay, so this is the format that we actually want to get a better number here than 15 years because we're looking for time and we'll essentially have everything there. We don't have K, but we can find it from this, right? So let's maybe start with that. So we can say K, doing a bit of algebra here, we multiply by K, divide by the 1/2. So K is equal to 0.693 divided by the half-life. And the half-life we know is 2.5 years. So let's go ahead and do the math there. So we have 0.693 divided by 2.5. So we get that number. So 0.277 units of inverse years for that. I'm going to move this over here now. Okay, so we found K. And then let's see, what else do we need to know? We need to know in final concentration and initial concentration. We have those up here, right? So initial is here. Final is here. So let's go and put those in. So we have natural log of our final, so 0.01 divided by initial 0.55. And we can go ahead and evaluate that because we know both of those numbers, and we can just get rid of the natural log when we do that. So 0.01 divided by 0.55, so we get that number, and then we do natural log, and we get that. Okay, so when we do that, we have negative 4. We'll call that 4.01. So that's that side of the equation. So we can say negative 4.01 is equal to 0.277 times t. So t would be, and there's a negative sign there, right? So I need to put that negative sign in. So t is equal to negative 4.01 divided by negative 0.277. Okay, so let's go ahead and do that. I'm going to go ahead and do divided by 0.277, and we have a negative sign there. Okay, So we get 14.47, or maybe we'll call that 14.5 years. Okay. So that is close to the number we got earlier. We would expect them to be close together, but it's not exactly the same. It's a little bit less than that, right? And we kind of anticipated that. You move this out of the way. We kind of anticipated that because this is less than 0.01. Now, how much less? We didn't necessarily know that. It's actually a half a year less. So 14 and a half years doing it kind of this more exact way, 15 years where we count the half-lives. So depending on the question, you might be expected to do it either of those two ways. So that is the little mini lecture for now. Next time we will start looking at temperature effects on reaction rates.